Thank you very much for the introduction and welcome everybody to this webinar. This webinar focuses on the efficiency of acoustic simulations. Specifically, we will introduce different techniques that will allow us to increase the efficiency of the analysis and will allow us to extend the simulation domain and the maximum frequency of the analysis itself. This is today's agenda. First, we will focus in detail on why we need efficient acoustic simulations. Then we will discuss on how to improve the efficiency of acoustic simulations in the low-mid frequency range, and then we will see how we can solve efficiently the mid-high frequency range. And finally, we will discuss if even ultrasonic applications can be solved. We will conclude this webinar with a demo and a Q&A session. So, let's start to discuss first why we need efficient acoustic simulations. To this aim, let's understand first why we should study acoustics and why we should do it by means of simulations. There are essentially three reasons for performing acoustic simulations. The first one is to accommodate standards defined by states or international authorities, which are becoming more and more restrictive. And this applies everywhere in any field that we consider. Also, the comfort of any product is important. It's a marketing argument today. If we consider, for example, a car, whatever is the market segment we consider, this is a primary problem. The third reason for performing acoustic simulation is for avoiding making prototypes. These are costly and involved late in the design process. So we have seen why we need simulations, but simulation needs also to be efficient. We can identify two reasons for this. The first one is concern the development cycle, which shall be as short as possible. Indeed, a short development time allows to be more competitive as we reach the market before the competition, and it allows to reduce the development cost. Then there is more and more the need for robust solutions, for example, for optimization reasons. In this case, several simulations are carried out, and also in this case, having efficient solutions providing results as fast as possible are mandatory. Now, how are acoustic simulations affected by these needs? To have results as soon as possible, acoustic simulations are limited to three aspects. They are limited on three aspects: the number of frequencies analyzed, the maximum frequency of analysis, and the maximum domain size. These limits affect, for example, the accuracy of the simulations and are strictly related to the computational capabilities available. To understand what kind of challenges we have to face when we aim at improving the efficiency of acoustic simulations, let's consider a generic frequency spectrum first. In order to improve the simulation accuracy, we have to first consider the low to mid frequency range. Second, we have to expand the maximum frequency or the domain size, although the limit between these two bands is not easy to find and it is case dependent. We will see in the next slides how to define this limit when considering acoustic propagation. And third, can we even simulate ultrasonic acoustics if we need so? Practically speaking, the computational limits from an acoustic propagation point of view are set by the number of degrees of freedom to simulate a problem, the solution method, and the computational resources. In other words, if we have certain computational resources available and specific solution method, we would have a specific limit we cannot exceed to have the solution in a reasonable time. On the other side, what is the computational limit? Can we identify from a physical point of view a parameter that can tell us if we can solve a problem or not? Indeed, we have spoken about the number of degrees of freedom, but practically it will limit either the maximum frequency or the problem size. These two quantities are related to the L to lambda ratio, where L is the dimension of the problem, whereas lambda is the wavelength of analysis, which is strictly connected with the frequency. In the end, the maximum number of degrees of freedom will limit the L over lambda ratio, and we might face the situation where to increase the domain of analysis, we need to increase the wavelengths, or, in other words, to increase the domain size, we need to decrease the frequency of analysis or vice versa. To increase the frequency, we have to reduce the domain size. If you use Actran Acoustics, for example, which is a standard FEM solver, most likely your computational resources available will allow you to solve problems up to around L over lambda ratio of less than 50 within a reasonable time from an industrial perspective with the current computational technologies. Before proceeding, as we have just spoken about Actran Acoustics, let me review briefly, for those of you who are not familiar with that, the Actran software suite. Indeed, Actran is an acoustic, vibroacoustic, and diacoustic software suites composed by different modules. The first one that we have already discussed is Actran Acoustics, which is a standard FEM module which allows the simulation of the acoustic propagation or radiation from weakly coupled vibrating structures. Then Actran Vibroacoustics, which allows to include the structural dynamic in the solution, so we can solve strongly coupled vibroacoustic problems. On top of it, we have Actran for trim body, which is a module specifically dedicated for interiors such as car compartments to efficiently analyze the effect of the so-called trim components. Then we have two other modules dedicated to the computation of the noise generated from turbulent flows. The first module is Actran Air Acoustic, which requires as input unsteady CFD. The second module is Actran SNGR, which requires as input steady CFD results compared to the former module. Actran SNGR provides approximated but faster analysis, as the input data have limited information from an acoustic perspective. Then Actran TM is a module dedicated to turbomachinery noise, and specifically it is useful for turbofan engine inlets. All these modules are standard FEM modules, so the solution scheme is an FEM method. Then we have Actran DGM, which is used typically for turbomachinery noise, but for bypass duct or exhaust where the physics is more complex. This is its first original development, but its efficiency allows to address the acoustic radiation for use domain or at very high frequencies. Moreover, this module features since 2015 the GPU acceleration, which allows solving problems previously unfeasible. Finally, Actran can be parallelized and feature a dedicated user interface. Today, we will discuss how to improve the computational efficiency in classic Actran Acoustics and Actran Vibroacoustic simulations, and we will illustrate the capabilities of Actran DGM for reaching much higher frequencies or bigger computational domains. Let's see now how we can improve the low mid-frequency range efficiency for acoustic simulations. And to this aim, let's discuss the acoustic mesh requirements for standard FEM simulations. Indeed, acoustic meshes are required to ensure accurate simulations. Therefore, a minimum number of elements per wavelength shall be ensured. Typical requirements ensuring good level of accuracy are 8 linear elements per wavelength or 4 quadratic elements per wavelength. For example, we see on the right a screenshot of Actran VI showing visually the quality of a mesh for a radiation problem, and almost everywhere 4 quadratic elements per wavelength are used, except close to the radiating structure where more elements are needed to better follow the geometry. It is worth to mention that these requirements are subjective, meaning that every user should evaluate if these limits shall be more or less restrictive for its own problem. Now let's compute a linear element size, for example. This is linked to the speed of sound, the fluid flow, and the frequency of analysis. This means that theoretically one mesh per frequency should be made. However, this is practically very rarely done, as this is time consuming from a user point of view. In other words, traditional acoustic calculations uses one mesh for all the frequencies for ease of use, and the computational time is basically equal for all the frequencies and driven by the mesh valid for the highest frequency, which is very fine, and therefore this is far from being efficient. On the contrary, adaptive acoustic calculations allows drastically improving the simulation efficiency. This technology exploits the so-called mesh adaptivity, where a set of meshes is created. One mesh for a given sub-frequency band is automatically built by the solver, targeting the maximum frequency of each band. Therefore, the computational time is extremely reduced, especially at low frequencies. At the same time, the user needs to provide only one mesh, or even only the surface mesh, as we will see in the following slides. The mesh adaptivity can be used for both interior and exterior acoustic components. Let's have a look on how we can use the mesh adaptivity for exterior acoustic radiations. The input needed is only the exterior wrapping surface of an object. Starting from this, Actran automatically creates a surrounding volume on the base of the thickness defined by the users. Finally, the code will simulate the far-field radiation by using either infinite elements or PML non-reflective boundary condition. We see below an example of a power train. The surrounding wrapping surface is given as input to the solver, which automatically creates a volume mesh, or it's better to say that creates a set of volume meshes and apply automatically the correct non-reflecting boundary condition on the exterior of this volume. If we have outdoor planes or baffled planes, these can be defined in the components and the mesh is created accordingly. Meaning that those outdoor planes, those baffled planes, can be below the object or can also cross the object. Moreover, noise sources can be placed in the far field, and this feature allows to define a diffuse sound field acting on the exterior component for taking into account the masking effect. Mesh adaptivity can also be applied to interior acoustic problems as well. For example, we have considered these car cavities solved directly by means of a finite field component. Also in this case, it is sufficient to provide only one mesh. Then a set of 8 meshes has been generated automatically to compute the interior acoustics up to 2000 Hz with a frequency step of 20 Hz. In this benchmark, the mesh adaptivity allowed to get a speed up of the model of about a factor of 4 with respect to a traditional finite element based approach, where a single mesh is built valid for the highest frequency and used for the entire frequency range. Speed up is obviously depending on the model size, frequency range, and so on, and the larger the frequency range, the better. So far we have seen the mesh adaptivity, which is a method for improving the mesh for low to mid frequency range. However, at a certain point, the number of degrees of freedom involved in simulations will be so high that we need a more efficient method to solve a problem. In this section, we will see how we can solve high-frequency problems. To this aim, the Actran software suite offers Actran DGM, which now can exploit the GPU acceleration for performing fast simulations. This technology enables solving very big domains or very high frequencies. So what is Actran DGM? Actran DGM is a time domain solver. It solves the linearized Euler equation and it provides results both in time and frequency domains. DGM stands for discontinuous hierarchy method, which combines the highly parallelizable aspect of a finite volume scheme to the accuracy of the finite element technique. Indeed, the degrees of freedom are stored at the element level. This means that the degrees of freedom are duplicated at the element interface, as we can see in the picture on the right. This duplication of degrees of freedom makes the method discontinuous, And this is a central aspect as it allows for an efficient parallel handling. These solvers use high element orders from 1 to 16 and automatically select both the element order and the computational timestamp. Originally, it was designed to solve acoustic propagation across non-uniform and rotational mean flow. Its computational performance are extremely interesting for solving large models and high-frequency models, so with an L over lambda ratio bigger than 50, as this solver is highly scalable. We can use hundreds of CPUs with relatively low RAM consumption. This code is also optimal for GPU multithreading. Indeed, now it supports the NVIDIA K40 and K80 GPU cards. So, originally, it was designed to solve acoustic propagation across non-uniform and rotational flows, but thanks to the efficiency and especially with the GPU acceleration, it is used in application even where the flow is zero, but for reaching high frequencies and simulating huge domains. It allows the radiation from a simple source, such as a monopole, or from a vibrating structure, or from a velocity boundary condition. It supports the radiation from time domain structural excitation, such as transient analysis performed with Nastran Sol 112, or it supports also frequency domain structural excitation, such as a dynamic analysis performed with Nastran Sol 111. Today we will see different examples of application in different fields. And as Actran DGM was initially used in the aerospace industry, I would say that naturally the first example we will see is in this industry. Although in this case this is not its typical usage. Indeed, we perform this computation for Airbus, and this case is related to an auxiliary power unit noise at the ground. The noise is generated by the power unit, and it is regulated because around the aircraft people are working, and therefore the noise levels cannot exceed certain limits. The challenge from a computational point of view is the fact of taking into account the exhaust, the jet of the exhaust, so a complex flow in terms of high temperature gradients and high velocity gradients. And also the other complex aspect is to take into account the geometrical complexities. In this simulation, the wings, the rear fuselage, the ground, and the vertical and horizontal tail planes have been considered, and the total volume simulated was about 8,500 cubic meters. This is an example of usage of Actran DGM, again for aircraft exhaust, but we presented this in cooperation with Airbus at the DAGA conference this year to demonstrate the benefits of the GPU acceleration. This example shows the performance reachable with Actran DGM and the GPU acceleration. With 2 GPU NVIDIA K40 cards, the simulation was about 29 times faster than a classic single-core computation. Let's apply now these methods to a real-life case. This concerns the simulation for meeting requirements set by pass-by-noise regulations. Specifically, pass-by-noise regulations limits the sound pressure level expressed in dBA. How does dBA work? To compute the sound pressure level in dBA, the A weighting curve is used. Basically, the A weighting attempts to account for the relative loudness perceived by a human ear, as the ear is less sensitive to low audio frequencies or very high ones. Concerning the pass-by-noise regulations, different sources in the vehicle can contribute to it: the engine radiation, exhaust or intake ducts, cooling fans, and others. These sources could be at low frequencies or at high frequencies. If the aim is to characterize the acoustics above 3,000 to 4,000 Hz, and the truck cabin is 5 meters long, we would have an L over lambda ratio bigger than 50, and therefore we can expect to have too expensive computation with a standard Actran acoustic analysis. For lower frequencies, we could use Actran acoustics, exploiting the mesh adaptivity. When we perform pulse binary computation, we need to specify the source. We have two ways to do it, either from a simulation or experiments when they concern the vibration level of a structure, for example, and we can perform the analysis of the radiation of a powertrain in Actran and import it, or perform experiments to get the vibration level on the powertrain and then import them. Another possibility requires to specify the monopoles instead of the real source to get the transfer function from the source to a specific location, or to determine the contribution of a source in a certain position. The source amplitude shall be determined experimentally by means of the inverse substitution monopole technique. In other words, in this kind of analysis, we are interested in both absolute noise levels or the transfer function the source and the receiver, between the source and the receiver, where the receiver position is located in the far field or around the vehicle surface. Any code we use to this aim shall allow to do this. For the low to mid-frequency approach, we have solved this problem and we computed the acoustic radiation from a monopole placed at the exhaust position around here. The mesh adaptivity, so first we have used Actran Acoustics and we have used the mesh adaptivity. The ground buffer plane has been taken into account automatically by the meshing tool. In other words, the mesh adaptivity has generated a set of meshes for the low frequency range and for higher frequency range. A set of 8 meshes has been generated, all of them featuring hexacore elements, allowing a gain of about 30 to 40% in terms of computational time and RAM consumption compared to the tetrahedral mesh. In this case, the computational gain was about 4 times faster than the case considering only one mesh for the whole frequency range. And it allowed to compute the acoustic propagation of this kind of model within 1 day. Thereafter, we have simulated the same case at a much higher frequency, at 5 kHz, and in this case the L over lambda ratio is about 70, and requires the use of Actran DGM with the GPU acceleration to be able to have the results in an industrial context. The model in total is 220 millions of degrees of freedom, and it was solved on a workstation equipped by 2 NVIDIA GPU cards K80. The computational time for one frequency is roughly 2 hours and 20 minutes. In the video we see the results in the time domain, whereas in the bottom of the slides we see the pressure maps. Finally, can we even do full 3D ultrasonic radiation? For example, if we consider ultrasonic proximity sensors, these are used to cover electric signals, to convert electric signals to ultrasonic waves and vice versa. Typically, these sensors are used to detect the distance from an object, and examples of application are very common in industrial equipment for automatic packaging, for instance. In aerospace, UAVs are making use of them, and finally in the automotive, these are used for parking sensors and also for future autonomous vehicles. We have done a simulation of a parking sensor with Actran DGM, where we have a full 3D analysis of a portion of the back of the car, where we have at a certain distance the object that we need to locate. The sensor radiates a set of very high frequency waves at 50 kHz. And one of the problems of these sensors is to be able to discriminate between the waves that are back reflected from the object and the spurious waves reflected by hardware such as the floor. In this case, the analysis involves roughly 1 billion degrees of freedom, and it was solved in about 15 hours. And here we can see the results. We have the waves that have been radiated and are back reflected. And we see here what is the problem. So basically, when the waves radiate, they impact the object, but also other objects such as the ground floor. Now, we are not interested in the response of the ground floor. We are interested only on the response of the object. And at the end, we need to discriminate between the back reflected wave from the object, from the back reflected wave from the floor. And this is all for this webinar. Thank you very much. If you have any question, don't hesitate to contact me.